Welcome to SciSense, where we unwrap scientific research, because science should not be a puzzle. All right, Mike, buckle up, because today we're going quantum. This paper is called Aharonov-Bohm Interference in Even Denominator Fractional Quantum Hall States by Kim, Dev, Scher, and colleagues, published in Nature. And it's about particles so weird they might be the key to building computers that never make mistakes.
Okay, you lost me at Aharonov. What are we actually talking about here?
There. So, you know how all particles in the universe come in two types? There's fermions, like electrons, that hate being in the same place as each other, and bosons, like photons, that love bunching together.
Sure, I guess. Like introverts and extroverts at a party.
Ha, exactly. But here's the wild thing. In the flatlands, in materials that are basically two-dimensional, there's a third type that physicists call anyons. And they're neither. They're like the ambiverts of the particle world.
Wait, that's allowed?
Only in 2D. It's a quantum physics loophole. And these researchers found the most exotic type, non-abelian anyons, hiding inside graphene. That's just a sheet of carbon atoms, one atom thick.
Okay, but why do we care about weird particles in flat carbon?
Because of quantum computing's biggest problem, errors. See, current quantum computers are like trying to build a sandcastle during an earthquake. The tiniest vibration, a stray photon, even a cosmic ray from space can destroy your quantum information.
That does sound frustrating.
So frustrating. But non-abelian anyons offer this wild solution. Instead of storing information in fragile quantum states, you store it in how the particles braid around each other. Like, imagine tying knots in string.
Knots? How does that help?
Because knots are tough. You can shake the string, poke it, whatever. The knot stays a knot unless you physically untie it. That's called topological protection. The information is protected by geometry itself.
Oh, that's clever. So local disturbances can't mess it up because the pattern is what matters.
Exactly. So the team built these ultra-precise graphene sandwiches, 2 layers stacked with extreme precision, cooled them to basically absolute zero, hit them with massive magnetic fields, and then watched for the telltale signature of these particles using quantum interference patterns.
And they found them.
They found them. The particles behaved exactly as theory predicted. When they moved them around each other, the whole quantum state transformed in that special, non-abelian way.
So we're one step closer to error-free quantum computers.
We are. It's still years away from practical use, but this proves the concept actually works in real materials. The era of topological quantum computing just got a lot more real.
Mind officially blown. Thanks, everyone. See you next time.
Thanks for listening to SciSense. Share it with a friend. See you next time.